In this video, we will explore convolution, which in the context of signal processing is the method to find the output of an LTI system to any input signal. We will focus our discussion on discrete time signals, but everything can be readily generalized to continuous time signals. We will develop the concepts of convolution from the ground up. Suppose that we have an LTI system, linear and time invariant system, which can take an input x of n and produce an output y of n. Well, there is a very important characterization of LTI systems called the impulse response. What this is very specifically when the input is a delta function, so just a function that is defined for all n, but is equal to 1 at sample 0 and 0 everywhere else, its output is going to be h of n, or the impulse response. So in other words, or to draw this rather, the input delta has an amplitude of 1 at sample 0 and a 0 everywhere else. So it's just this impulse. And due to this system, it produces an output which I'm going to make up. This completely depends on the actual system. So not knowing anything about the system, I'm just going to make it up, and I'm going to say that it's equal to these three impulses here, these three samples at 0, 1, and 2, and is 0 everywhere else. So this fully characterizes our LTI system. We have an input of a delta, which is just again a single impulse of amplitude 1 at sample 0, and we see what its output is, the impulse response. The reason that this is so powerful is because we can compose any signal x of n out of shifted and scaled versions of the delta function. And since we know that the system is LTI, linear and time invariant, we know that the output to this is going to be the same shifts and scalings of the impulse response. So let's analyze this through a pictorial example. Suppose that we have an input signal x of n, which is going to be -1, +2, and 1. So this is at sample -1, 0, and 1, with amplitudes of -1, 2, and 1, and is 0 everywhere else. This can be decomposed into three delta functions that are shifted and scaled. Specifically, this is going to be -1 times delta of n plus 1. The first component, which is going to be just a delta shifted to the left by 1 and scaled by -1. So it has an amplitude of -1 and a 0 everywhere else. And we can also see that this can further be written as x of -1 times delta of n plus 1, because x of -1 is -1. The next component that makes up our original x signal is going to be 2 times delta of n. So it's just going to be our regular delta function, not shifted, scaled by 2, so therefore it has an amplitude of 2 and a 0 everywhere else. And of course this can further be written as x of 0 times delta of n. And the last component is going to be just 1 times delta of n minus 1. So we shift things over to the right by 1, scale by 1. It's equal to 1 at 1 and 0 everywhere else. And once again, this is x of 1 times delta of n minus 1. Now we're going to use the impulse response, which I defined up here, in order to find the system response to each one of these components individually. So this one over here is going to be the same thing as scaling the impulse response by -1 and shifting it left by 1, since the system is LTI, and this only holds for LTI systems. So this is going to be this shifted to the left by 1 and scaled by -1. So it's going to look like this. All of these are at amplitude -1, and they're at sample -1, 0, and 1. And what this is the same thing, the same scaling as here, and the same shift as for the delta of h. So therefore, it's going to be x of -1 times h of n plus 1. That's what this signal is, using the h from up here. Likewise, this next signal, just a single delta that's scaled by 2, that's going to be x of 0 times h of n with no shift. And so therefore it's just going to be a scaling of the original h, making it equal to this signal here, which has an amplitude of 2, since x of 0 is 2. And of course, I keep on omitting this, but it always holds that the function is defined for all values of n. They're just 0 outside of this range. And finally, the last signal is going to be x of 1 times h of n minus 1. And so we shift our h to the right by 1 and scale it by 1. So therefore, it will be just a shifted version of h. At an amplitude of 1. Now, we use the fact that this is an LTI system, and therefore a superposition of inputs should create the same superposition of outputs. We can use the fact that adding up these three scaled and shifted deltas gives us our original x. We can therefore add up these three shifted and scaled h's in order to create the total output to our complicated signal x. So we add up all of these. We're going to add this, and we're going to get a total system response, which is just going to be adding up each one of these point by point. So everywhere beyond -1 is going to be zeros. At -1, the only component comes from here, and so that's going to be at an amplitude of -1. At 0, we get -1 plus 2, so it's going to be 1. At 1, we get -1 plus 2 plus 1, so that's going to be an amplitude of 2. At 2, we get an amplitude of 0 from this one, 2 from here, 1 from here, so that's actually going to be 3. And then at 3, the only contribution left is going to be from this signal here, and that's going to be a 1. And that's it, zeros everywhere else. So we can label this as 1, 2, 3, and 1. And this is the full system response y of n, which is made up of these individual component scaled and shifted versions of the impulse response, since that corresponds to the components that created our more complicated signal x. Now we can see a pattern that emerges here. We can see a pattern of what signals we had to add up in order to find this general response, and we can write it. We can write it as y of n is equal to, well, in this case we see that it's x of -1 times h of n plus 1 plus x of 0 times h of 0 plus x of 1 times h of n minus 1. And in general, we can see that y of n is going to be made up of components of this type for any given signal, depending on where x was originally defined. So this is going to be plus, going from whatever it started at arbitrarily low, x of -9 times h of n plus 9 plus x of -8 times h of n plus 8 And we keep going, and this can go on for, of course, positive values, x of 7, h of n minus 7, and we keep going for as long as we have this defined. So in this case, it was only these 3 points, but in general, it can hold for any points. And again, more generally, just to write this for all possible combinations, taking everything into account, we say that this is a summation going from k equals negative infinity to infinity of x of k times h of n minus k. And this is the definition of the convolution sum. This gives us a mathematical form to find the response to any arbitrary input x when we know the impulse response of the system and the system is linear and time invariant. So this kind of an example worked well with pictures when it comes to a pretty simple input signal x. We only have 3 samples here, and therefore we add up 3 scale shifted versions of h to get our output y. However, what happens if x is made up of 20 samples or 100 samples or maybe even infinitely many samples if it's defined as a function? In that case, we can't draw that many different versions of h and just add them all up. It wouldn't make sense practically. So instead, we take a more mathematical approach to convolution, which I will address next. The entire mathematical approach is centered on the definition of the convolution, which we just proved using our pictures. Now for this particular example, I'm going to choose x of n equal to 1/2 to the n plus 1 power times a unit step function of n minus 2. And in case you haven't seen a unit step function before, what it basically is, let me draw it over here, the unit step function is equal to 1 for all values of n greater than or equal to 0, and 0 for all values less than 0. This is the unit step function, and so here I'm saying that I'm taking this unit step function and shifting it to the right by 2 samples. So now it starts at 2 and goes on for all infinity, and 0 for everything before that. So this basically limits my n to values that are greater than or equal to 2 in order for this function to converge. H of n, the impulse response of the system, I'm going to define by u of n plus 3. So another step function that starts at negative 3 now. Now we're going to do everything mathematically, but it still is a good idea to draw pictures at this point because they're going to keep everything straight for us. They're going to keep track of everything that we're doing. Because what we're going to do is we are literally going to plug things into this equation, but we have to know what we're plugging in and summing, and we're going to do that by drawing these pictures. So first, let's start by drawing what x of n actually looks like. We say that it starts at 2 because we're multiplying by 1s, starting at 2, at n equals 2. And we're going to have this function 1/2 to the n plus 1. So therefore, the first sample here is going to have a value of 1/8, because that's 1/2 to the 3, to the third power, n plus 1, because it starts at 2. And then it's going to be this decaying exponential kind of function, which could look something like this. And it keeps going for all infinity and is 0 for everything to the left. Our h of n is even easier because it's just going to be 1s starting at minus 3. And that keeps going for infinity and 0s everywhere else. And all of it at an amplitude of 1. Now, what we have to do next is to construct the signal h of n minus k. Currently we have h of n and x of n. We need x of k and h of n minus k. Well, one thing we can do that's kind of trivial is to construct x of k. So this first one here was x of n. And to construct x of k, well, it's exactly the same thing, except now my variable along the x-axis is k instead of n. But I'm going to draw it anyway because those are the signals that we're actually interested in, x of k and h of n minus k. Now, h of n minus k is going to be a little bit harder to construct. We'll do it in 3 steps. First, we're going to draw h of k, and that's going to be the exact same thing as we had before, except now we have k on the x-axis. The next thing is to make h of minus k. That's just a time reversal, so therefore we're going to just reverse this about the y-axis. And therefore we're going to get a signal that is defined as 1s up to the point 3 and as 0s everywhere beyond. And as 1s going backwards for all infinity. So that's just reversing this h of k to make it h of minus k. And the next step then is to create our h of n minus k, and that's just going to be a shift by n of the entire h of minus k. Now n in this case is no longer the variable along the x-axis, but rather you can consider it to be a constant for the purposes of drawing this function. So what this will look like is it's going to be something like this, where we have our h of k, and this is h of minus k, and 0 everywhere going to the right, and 1's going everywhere to the left. But the initial point over here, this point is no longer at 3, but is rather at n plus 3, because we shift the entire thing by n. And so this point is n plus 2, n plus 1, n minus 1, n minus 2, and so on. So now everything here is in terms of n, and this is our function h of n minus k. In this case, I drew it arbitrarily for n is a negative number because everything is before this y-axis. I could have also drawn it for n being other values, and it could have been in front. But what we're going to do is we're going to follow along exactly with our definition of the convolution, which is right here again. And we're going to then take on values of n going from minus infinity to infinity. In other words, what we want to do is define the function y of n for all values of n. Now, as I mentioned, n can be treated as a constant within h of n minus k, because in this part, for every value of n, I fix a value of n, and I perform this summation across all k. And this will become more clear once I start actually drawing these pictures. So what we're going to do is we're going to examine what this looks like for various values of n and perform that actual summation. Let's suppose for this first part that n is equal to minus 3. In other words, we want to find the value of y of negative 3. When n is equal to negative 3, we can draw our functions as follows. So we still have our x of k, which begins at 2 and is this decaying exponential, and is zeros everywhere before that. And right below it, I'm going to draw h of n minus k. In this case, we know what our n is. It's negative 3. And therefore, negative 3 plus 3 is 0. And that means that our function looks like this. And this goes on, and it zeros everywhere beyond. Because remember that our h of n minus k has its first point over here at n plus 3. So when n is equal to negative 3, this whole thing is at 0. It starts at 0. So this is the picture that we're going to be looking at. And remember, again, what we're trying to find here, what we're trying to use, is the summation from k equals minus infinity to infinity of x of k times h of n minus k. So at this particular point, so this is the general definition for y of n. We're looking at y of minus 3. We fixed n equals minus 3. So therefore, this is going to be the summation from k equals minus infinity to infinity of x of k times h of minus 3 minus k. Well, we just drew this over here, h of minus 3 minus k. And we see that what we're going to do is literally multiply these two functions together and sum them across all k. Well, let's multiply them point by point. Since this starts at 2, and the value at 2 of h of n minus k is 0, this is going to be 0. In fact, all of these values of x of k are going to be multiplied by 0 because the function h of n minus k is 0 beyond k equals 2. Likewise, for all places where h of n minus k is non-zero, x of k is 0. And therefore the product is going to be 0. And if we sum across all k, we're going to get a total of 0. So this whole thing is equal to 0. In fact, we can generalize this and we can see that it's going to hold when n plus 3 is less than 2. This is going to give us no overlap between h of n minus k, since this first point is at n plus 3. When it's less than 2, there will be no overlap between x of k and h of n minus k, and therefore we're going to get that y of n is equal to 0, because there is no overlap between x of k and h of n minus k. This can also, of course, be written as when n is less than negative 1, since n plus 3 less than 2 is the same thing as n less than negative 1. So then what happens when n plus 3 is greater than or equal to 2? Well, again, let's start by looking at a single example. Let's say that n is equal to 1. So we have our x of k, which hasn't changed, but when n is equal to 1, our h of n minus k will change, because now when n is equal to 1, n plus 3 is equal to 4, and therefore our function is going to start at 4. So it'll start over here and go backwards, and so on for infinity, and zeros everywhere beyond. So this is at 4, because this is equal to h of 1 minus k. So once again, we can take a look at y of 1. Since we fixed n equals 1, we're looking at y of 1. That's going to be the summation from k equals minus infinity to infinity of x of k and h of 1 minus k. So again, we're looking at the product of these two functions, and that will be just the places where they overlap. And they only overlap in 3 locations, at k equals 4, 3, and 2. So in fact, since everywhere else is going to be 0, the only places where we care about are going to be from k is equal to 2 up to 4. And we're going to multiply our functions. And we can see that it's just going to be, since h of n minus k is just 1s everywhere where it exists, it's just going to be the corresponding values of x of k that are going to get added together. So this is going to actually be, since x of k is defined as 1/2 to the n plus 1, this is going to be 1 over 2 to the 3 plus 1/2 to the 4 plus 1/2 to the 5. Or, if we just kept it in the original summation notation, it would have just been 1/2 to the k plus 1 times h at those locations, which is just equal to 1. And this is the same thing. Now, how can we generalize this? Well, we can see a pattern. As n keeps increasing beyond 2, or rather, as n keeps on increasing beyond -1, or n plus 3 increases beyond 2, as that leading point goes beyond, we're going to sum up all the contributions from x of k from 2 up to that leading point, because everywhere beyond that it's 0 and everywhere before that it's 0 for x. So in general, then, for n plus 3 greater than or equal to 2, we get that y of n is going to be equal to the summation. And again, it technically goes from k equals minus infinity to infinity, but the only places where it's going to be non-zero, where there's overlap, is starting from k equals 2 up to this point, which is just n plus 3. And it's going to be x of k times h of n minus k. And so in this case, that's going to be from k equals 2 to n plus 3. X of k is defined as 1/2 to the k plus 1. H of n minus k is always going to be just 1. And that's it. We can write this as a closed form just by using some math, but that doesn't actually matter. The part that's important is being able to write this summation and understanding what it means. We, again, literally multiply together the overlap parts of the functions that correspond to non-zero values and add their contributions together. So in this case up here, it'll be just these three values which we're adding together, because everything else gets zeroed out. Now the full solution to the problem is not quite this, because remember, we had defined y of n to be equal to 0 for n plus 3 less than 2. And in this case, this is the same thing as writing n is greater than or equal to minus 1. So the full solution to the problem is actually that y of n is equal to 1/4 minus 1 over 2 to the n plus 4 times the unit step function of n plus 1, which means that it's a unit step function that is defined from -1 forward, and everything else before it gets zeroed out. And that is the solution to our total function. And as one last step, let's draw what this looks like. Again, it'll be zeros for every value before -1. At -1, according to this equation, we have a value, and it keeps on going something like this. Without defining actual values, we can see that it starts at -1 and keeps on going for all infinity onwards. So this is what the entire function y of n looks like. Now the important parts to remember here are that we evaluated this function for every value of n. We had to perform this infinite summation. So we fixed a value of n and solved the summation for that value. But what we found was that there's a pattern that exists. We can find this nice form of the summation over here with these bounds that are defined by the areas which have a non-zero overlap between x of k and h of n minus k. And therefore we can write this in a more compact form and actually solve it. Instead of trying to find the value for each individual value of n, we wrote it as a function of n. Altogether, we have seen where convolution comes from and how to use it. We saw that the convolution sum is a direct consequence of the LTI property of systems and allows us to find the response of the system to any arbitrary input, all by knowing the system response to a simple delta function. This is not generally true for non-LTI systems and is the reason that LTI systems are so good for analysis.